Okay, if we have a rectangular parallel test, then you think of this as maybe having the base in the XY plane, and representing, well, we don't worry about what it represents, we'll represent it in a minute. Okay, so it has dimensions 3 by 2 by 7. Well, we know how to calculate the volume. So people use length times width times height, which is all right, but that's not how we want to think of it. We want to think of the volume as being the area of the base times the altitude. It comes down to the same thing, but this is a more general idea here, okay? And this would apply to a cylinder, a circular cylinder, elliptical cylinder. It applies to any shape that has a consistent altitude above a base. So it could be a polygon in the base, hexagon, could be some kind of irregular shape. Wouldn't matter. We can take the area at the base and multiply by the altitude and get the volume, as long as it has a consistent altitude. However, things don't always have consistent altitude. Now we come back to this guy, our favorite. Okay, take a good close look at it and then try to get it in the camera. And if this is sitting in the XY plane, then if these altitudes here represent the values of a function, then the volume of this thing is pretty close to representing the volume defined by that function, okay? Problem here is we don't know what altitude to use to approximate the volume. So what we're going to do is we're going to say, well, if this is our shape, we take any sample point in the region of the base, okay? In the region of the XY plane, any sample point within this rectangle, and we can find the height here, the altitude, and use this for the altitude. It doesn't much matter what sample point we use. We get something pretty close to the same thing. Of course, the way this is drawn, you know, this altitude is a little less than this, is quite a bit less than this. So there might be a 20%, 15% variance in what you would get for the altitude depending where you choose the sample point. So you're not going to get a great approximation, but we still say we get some kind of an approximation of the volume if we multiply the area of the base by the altitude. Okay, now here we have a rectangular region in the XY plane. There's a Z, comes out this way. We're not going to worry about the Z just yet, but it's there. Okay, so we have a graph of some function lying above this rectangle. Okay. If we subdivide this rectangle, into a bunch of smaller rectangles, okay? And we do that if this is, let's say, x equals A and x equals B. We partition the x interval from A to B by the partition A, I guess I better write it down here, it's kind of long, equals x naught, which is less than x1, which is less than x2, which in general is less than xi minus 1, less than xi, and then finally less than x sub n, which equals b. Well, then we see you know, here's x1, x2, x3, x4, x5, x6, corresponding to these vertical strips. Okay? Now each vertical strip would be one of these, except it'd be very elongated. There could be a lot of variation in the values of the function between a point down here and a point up here. Okay? And there'd be all kinds of variations between here and here and here and here. So we could try to approximate the volume above each one of these strips, but there'd be a lot of variance. Okay, there'd be typically a lot of variance between the low point and the high point of the strip. So what we do is we partition Y. Okay? So in doing that, we break this up into small rectangles. And on a small rectangle, if the rectangle's small enough, there's not going to be a lot of variation in the height. You know, the position down here doesn't change by enough to make the z coordinate or the value of f of xy change by very much. Okay? So on any one of these, we get a good approximation. Okay. And then we shrink our grid size, our mesh size. In other words, we partition. You know, we use a finer and finer partition on X and a finer and finer partition on Y. And we add up all the volumes that we get. And that gives us a pretty good approximation. And in the limit, if the function is well behaved, doesn't have big jumps, continuous basically, and so forth, then in the limit we get the actual volume of the surface above this rectangle. Okay, so we partition Y. And I'm not going to write out the partition, but it's going to be, this could be C and D. So C less than or equal, C equal to Y naught, less than or equal to Y1, and so forth. Actually, it's worth writing this out. Y partition now, gotta learn not to write what my eye catches. So this is C and this is D. This would be the Y partition. Okay, Y naught equal to C, Ym equal to D, because we don't want to restrict the number of intervals we get in this partition to be the same as the number of intervals we get in this partition. It will generally be different. And for notational reasons, we want to use M here, where we have M here. Okay, at least we need to use two different numbers, or two different letters for these subscripts. Also, we use J for the typical index on the Y's, because we want to be able to talk about the interval from xi minus 1 to xi and the interval from yj minus 1 to yj. We don't want to have We don't want to just talk about xi minus 1 to xi and yi minus 1 to yi, because then the number of the partition, or the number of the interval you use here, is the same as the number of the interval you use here, and it doesn't generally describe the intervals. Okay. So, in other words, if I want to do this interval here, then I've got my x I minus 1 and my xi here and here. And my y j minus 1 and yj here and here. So now I can talk about what happens on this interval. And if my partition is small, the values of the function are pretty much not all exactly the same, they're all very close to being the same. Okay, so in a small increment, the values of z equals f of x, y don't vary much. I should say they don't vary very much, but that's confusing. Okay, so I'm going to use blue for a sample point. So if I choose my sample point here, and I get an altitude up here, it's not much different than if I do a sample point over here, or over here, or over here. I'm going to use a notation here. Okay, I'm going to call this sample point xi star yj star. And it's going to be the same for any sample point xi star yj star with xi minus 1 less than xi star less than xi and yj minus 1. Well, yj star between yj minus 1 and yj. And all this means is that, here's my xi star. it's between xi minus 1 and xi. And here's my yj star. So here's my sample point. Xi star, yj star. Here it is inside the approximate rectangular solid that you get when you approximate the function, or when you confine the function to this rectangle. Okay. I should say confine the function to the region above this rectangle. Confine the domain of the function temporarily to this rectangle. Okay. Well, that's kind of an overview of what a double integral is. Okay. You set up integrals by partitioning and taking limits. You make a double integral by partitioning for a single interval, for a function of a single variable, you just partition say the x interval, or the interval of the independent variable. Okay, here you've got to partition both the x and y intervals, but we can see that if we add up all the volumes here, we're going to get something that's pretty close to the volume of whatever lies, well, the volume underneath the graph of the function and above this big rectangle. Okay, well, that's the essence of a double integral, but how's it going to work out? So we're going to talk about that a little bit.